Okay, so now let's look at our first elastic collision example. And it's the classical one of having two balls of, let's say, same mass and collide, and what happens next. Okay, so just like on a pool table, two billiard balls collide usually with the same mass, all right? So to do these problems, always start with drawing a diagram, and the tip over here is draw two diagrams, okay? Draw a before and after, okay? And that allows you to label all the variables you need, okay? So a lot of times students always ask, should I draw a diagram in physics? The answer is always yes. All right, there's always no harm in drawing a diagram. The diagram is really it serves one purpose that a lot of students don't realize that is important, is it helps you define the variables that you're going to use later on, and allow the TAs or graders to know what you're talking about, and be able to give you partial credits. Because if we cannot tell, if you just invent a symbol out of nowhere, unless you state it in words. So you have two choices. You can either say, for example, before, what I'm going to do is write this ball and this ball, and I can say, hey, let the initial velocity of ball A be UA. I can do it like this, or I can just write UA over here. Okay, so which one do you prefer? Do you want to write out a sentence, or do you want to draw a diagram? I prefer drawing a diagram. Okay, if you don't do either of them, and you make a mistake and you get an answer, you may not get any partial credits, because if you say UA, someone else is going to say, hey, I don't like UA, I like the initial A, right? So so your UA, no one knows what it means unless you define it. All right, but we are not English majors, so we don't need you to write essays. So if you draw a diagram and it's clear that what it means, that is good enough. We're very visual people, so that's fine. All right, so so this guy has MA, right, and this guy has MB, and UB equals to 0. Okay, and afterwards, I don't know what happened. Let me draw the general case first. The general case is afterwards, this guy is moving, this guy is moving. Okay, so I'll call it VA, VB, this, okay? And I want to find out what happens over here. This is my goal, all right? The mass doesn't change, we'll label that as well. So collision problems, the tip is draw before and after like this, okay? And here it's usually some given numbers, let's say 5, but 5 meters per second. But I will try to not plug in the numbers until the very end, work with variables. Also, number one, give you, you should do the same. So you train yourself to get good at algebra. A lot of students ask, I'm not good at algebra, what can I do? Well, train yourself. The more you do it, the better you will. If you try to avoid it, you will never improve. All right, so that's a general tip. Also something very deep over there, so remember that. Okay, so another issue is, I forgot what I was going to say. I'll come back to it. So draw your before and after diagram before you set up your equations. And yeah, I'll plug in the numbers last. We'll see what we have over here. Oh, yes. Now remember, is how do I know they are both going this way? Especially, well, B, maybe I can imagine after you collide. Yes, B is probably going to go that way. But how do I know if A is going to go that way, if it's going to, or is A is going to get recoiled, like hit B and then get bounced back? Or maybe just stand still, right? And so is the velocity that way, or 0? Now, it doesn't matter, because I'm going to treat everything as vectors. It's a one-dimension vector, so it has positive and negative value. If it's going the other way, if I get a negative number, then it just means that it's going the other way. Okay, so let's say if I solve it and then I find, oh, VA equals to 2, now I know that it's going that way. If I solve it and I find VA equals to -3, I know that it's going that way. Okay, because velocity is a vector and we are treating it as a vector, okay? Just like in your SUVATs, right? After you solve it, and then if you define your axis, oh, I should define my axis as well, but so positive x to the right, right? So just like a SUVAT, you can define a positive going up, right? And then you solve V, oh, V is -5, that means what? That means it's going down. Or if you define your axis this way as positive, and then you calculate something, and then you find, oh, S is -5. What does displacement equals -5 mean? It just means it went up because your axis was going down. Okay, so negative numbers are fine when you treat them as proper vectors. Okay, right. So yeah, let's go ahead. So well, what can we say? So we are told that this is, you have to be told that this is an elastic collision. That means there's no energy loss, and that what that means is elastic, right? You can immediately write down kinetic, and so K total initial will equals to K total final. Okay, so kinetic energy is conserved. Momentum is always conserved in any collisions that doesn't have an external force. So all the forces are, the collision is all internal in the system. Okay, so my system is both A and B together. So there's no extra force moving on them. So no friction in other words. Right? Okay, so what do we know? We know conservation of momentum. I'll call it COP, conservation of momentum, P for momentum. And conservation of energy. So write down these two. The reason I don't do COM is sometimes that's abbreviated for conservation of mass. Okay, so that the fact that mass is not created or destroyed. So that's not what I'm referring to. So I sometimes abbreviate as COP. All right, so conservation of momentum tells me the initial momentum, if I add it up, so MAUA plus MBUB should equals to the final. So MAVA plus MBVB, okay? And conservation of energy, so let's call that equation number 1. And conservation of energy tells me 1/2 MAUA squared plus 1/2 MBUB squared equals, right? Common issue with people is they don't write MA and B, they just write 1/2 MU squared. And without the subscripts. And again, we cannot give you points for that because we don't know which M are you talking about. So defining your variables, if there's one key takeaway about physics, solving problems, skills is that you can carry forward. Like you might not use this exact equation again in 3B and 3C, but one thing you will use is how to set up your problems and careful of defining. Make sure you define variables, draw diagrams, define your variables before you use it in the equation. Very important to get points. And not only if you say, I don't care about exams, it's about readability. It's about how to present your work, present your logic to professionally, right? Okay, so 1/2 MAVA squared plus 1/2 MBVB squared. Okay, so I'm going to call that equation 2. All right, so the problem can have different masses. In fact, later on, try to solve it with the same problem with different mass. I'll drop down this as exercise, right? So let's say MA equals to 2 kilograms and MB equals to 3 kilograms. See what happens. So this is your exercise. I will solve a case first, just to see if you know how to manipulate the equations. But I want to know, for example, one of the simple case first is if the mass is all the same, right? So if these two are the same. So I'll solve MA equals to MB. Okay, so I could call them M. It could be any value. Turns out it won't matter what the M is. So it could be 2 kilograms, 5 kilograms, whatever. But just the fact that they're the same. Okay, so one will now equation number 1. If the masses are all the same, they will all cancel, and they'll tell me UA plus UB is VA plus VB. All right. So the sum of these speeds are the same as the sum of these speeds. Notice this is also 0, and this is 5. I could plug in 5 plus 0, right? So this is 5. So it means this plus this is equals to 5. But I'm not going to plug in the numbers just yet. So let's try to learn something general, because if I plug in the number, then in the next case, if I change the numbers, I'll need to do the whole thing all over again. So I want to try to see if I can plug in the number last and see if I can learn something general, something deep, so I don't have to do something again, and I can just plug in the numbers or change the numbers that I need to plug in at the final step. So that's the benefit of doing that. So here, equation 2 will tell me m's are the same, right? So they all cancel. The 1/2 also cancel. So that tells me UA square plus UB square equals VA square plus VB square. Okay. What can we say over here? Let's move this over to this side and this over to this side and see what we can say about this. And same thing with the top. So I'll move all the A's. Let me just add an extra line in between so I can maneuver them. So I want to put all the A's together on one side. Just before I forget, copy this first. equals to VA squared plus VB squared. Okay. So we basically need to find ways to simplify this equation. So there's a couple of ways to go. One way is to move everything to the same side and see what we can do, right? So UA minus VA is equals to VB minus UB. Okay, and over here we have UA square minus VA square. So everything that's about A, I'm going to put it to one side, and everything that's about B, I'm going to put it to the other side. Okay, so what can I do to combine these two equations? Now I know that I see there's a difference of two squares, and we can use a useful identity if you remember. If I do A plus B times A minus B, that's A squared minus B squared, right? If you forget that, this is very useful to remember. So A plus B times A minus B is A squared minus B squared. Okay, so it's the difference between two. Which one minus which one depends on which one minus which one here. Okay, the quick proof, right? So A times A is A squared, A times B is minus AB, B times A, right, is plus AB, and then B times B over here minus B squared. But you have plus AB and minus AB, so these precisely cancels out, right? And you just have A squared minus B squared. So a very useful thing to remember. Okay, very useful. Put that in the box. You can take note of that. So that means just from this identity, this is an mathematical identity, you can write UA plus VA times UA minus VA. And same thing here, you can do VB plus VA, VB minus VA. Okay. Should one of them be U? Let's see. UA minus VA and VB minus UB. There we go. UB. That makes more sense. So this would be UB. Yes, everything A on one side, everything B on one side. Yes, that makes more sense. Yeah, good. Okay. So now, can you see something we can plug in? This is the same as this, right? So I can now replace what I underlined with this. Okay. So we have UA plus VA times VB minus UB. VB plus UB, VB minus UB. Okay. And now you also spot this is the same as this. Okay. And that means these will cancel out. And this tells me UA plus VA equals to VB plus UB. Okay. Right. So what have we found? Let me call this equation 3 and equation 4. So we find that the difference between UA and VA is the same as the difference between VB and UB. So that's the initial and final velocity, right, of A. The difference between that is the same as the difference between that. And the difference, the sum of them is also the same as the sum of the velocity, okay? So what is my goal? My goal is to solve VA and VB. What am I given? Let's check out what am I given. Usually I'm given the initial state to predict the final state, right? We want to predict what happened to the motion. So usually we're given initial conditions. So we're given U's and we're given the U's, right? So how many unknowns do I have? I have 2 unknowns and 2 equations. So now we can go about and solve them. Okay, so yeah, so let's do it here. So I have equation 3 and equation 4. What did I want to do is I want to solve for VA and VB. One of them is minus, one of them is plus, right? So again, it begs you to just add them together, because if you add them, you successfully eliminate VA, all right? So let's try that. So if I add 3 and 4, so 3 plus 4 will give me, on the left-hand side, it will give me 2 UA. On the right-hand side, when I add this to this, you've seen me use this trick enough times now, then the UB cancels out. So I just have 2 VB. What does that tell me? That tells me UA equals to VB. Okay, what is my goal? My goal is to solve VB. So let me put that on the left. VB. Yeah, let me write that just so you'll do this in an exam as well. Write this vertically instead of horizontally. It's usually more traceable, right? So they use cancel. So VB equals to UA. Okay. Well, so I know UA is 5. So now I know VB is 5. Okay, I've solved one. Now I need to solve VA. So what we can do is subtract this, take this and subtract this. Okay. So 3 subtract 4. 4 subtract 3 would be better, but let's say you don't know. Yeah, actually doesn't matter. Yeah, so I want to get rid of, my goal now is, so I found VB, right? VB is equals to UA. And now I also want to find VA. So to find VA, I want to get rid of VB. So if I subtract one another, I'll get rid of VB. Right? So let's take 3 subtract 4. I said 4 subtract 3 is better, is because if I take 3 subtract 4, I get double negatives, but that's okay. All right, so this subtract this, the UA goes away. Then I have minus VA minus VA, so minus 2VA equals to, here the VB goes away, and then minus UB times minus another UB, so 2UB over here, okay? So the 2 will cancel out, so VA equals to UB. Okay, what was UB? 0, okay? So now VA is 0. Okay, the reason why I still don't plug in, I mean, now I can plug in the number and you can see I got the answer essentially, but now I learned something even more general, is the new B velocity is the same as the old A velocity. So B, if they're the same mass, I'm using here, right? To do everything over here, I use MA equals to MB. So the moment I went from this arrow to this side, I'm applying MA equals to MB. If that's the case, the velocity transfers, right? Whatever UA was, now it's the new velocity of B. And whatever the old velocity of B was, is now the new velocity of A. Okay, so A just took B's original velocity, which is 0, and B took A's original velocity, which was 5. Okay, so if this guy stands still, so let me just be clear, right? So now that's plus 5, and that's 0. Right, so now we got that 0, that's 5. So if this is still, this is coming over, this is at rest, this is coming over, it hits this. Now A stands still and B moves at 5, right? You've seen this in billiard ball tables where it's almost perfectly elastic, as close to elastic as possible, so there's no energy loss. There's obviously sound, but it's very little. Yeah, you've seen this probably happen. And this famous toy called the Newton's Cradle, which illustrates this perfectly. And let's see if I can bring this up. You will have seen this before, right? You'll see that this is exactly what happens when they collide. Now, this is more complicated with a couple of objects, but you can do it with just 2 and see what happens. So they're obviously the same mass. And when you hit over here, if you stare at the middle, it's almost like magic. The other stays still. Now there's heat loss to friction and everything. So after a couple of cycles, they don't go too perfectly. The other guy doesn't stand perfectly still, as you see, but it's still pretty cool, pretty close to what we have. So this is the result of conservation of momentum and conservation of kinetic energy together. Okay, so we'll see that for one more time. You see at first, when there isn't too much heat loss just yet, it's pretty perfect. The other guy is standing still. So we have exactly that result. Okay, so the velocity sort of transfers from one to another, and you can go about and try, what if the masses are different? What will happen? Okay, there's a YouTube video as well. If you Google Newton's Cradle, it's like a cradle. I don't know if Newton's built it or it's just a toy that we invented now and just honor Newton with his name. You can find that out as well. But there's another YouTube video on different masses, Newton Cradle with different mass. You can look that up and see if it confirms what you solve. Okay, so let's try to find VA and VB using different mass. Obviously, the algebra would be different. But essentially, you're looking for two equations. Which two equations? You have conservation of momentum, conservation of energy. So you have two equations and two unknowns. So everything should be solvable. Okay. All right. So next we'll look at an inelastic collision example.